Hello, everybody, and welcome back. Let's say, for the purposes of today, that you are a data scientist. Congrats, by the way. And you're tasked for going into a high school and looking at all the connections that students may have. And the data that we're going to be looking at today will be a survey that's handed out to everybody in the high school, and they list out all the different friends that they have. And then their friends did that, and their friends did that, all the way down the line. And so you have, for every student in the school, a network object. And if you don't remember how to put that together, you can go back and revisit the last video, because that's where we kind of talked about network objects and network data. But you could set this up in many different ways. You could do the bipartite thing and say, well, I go to these classes and I'm a part of these activities, therefore I'm connected to those activities, and everybody else is therefore connected to those. We're not going to get that into detail today, but we're just going to do a straight up edge list network object of friends. But the school administrator isn't really interested in the network object. They're more so interested in whether or not popularity in this network and how many connections people have relates to things that the administrator may care about, like school violence or test scores, of course. It always comes back to test scores, or just participation and attendance, or just feelings of happiness, or socioeconomics, if you're able to get that information. Or like parts throughout the city that people may live. Any number of those things the school administrator may care about. So today we're going to be talking about measures of centrality. And centrality in the degree sense can be seen as just a popularity statistic. Know that the word popularity is a little bit troublesome. Like if it's a network of people that hate each other, is that still popularity? I guess. But popularity can be interpreted in a couple different ways. But degree can't. Degree is just the number of people that you have connected. And you can have outward degrees or inward degrees. We're also going to move beyond and talk a little bit about page rank. We're going to talk about betweenness and closeness, and eigenvector centrality. There's a lot to get through. So the R notes are all on GitHub. You can go through there and read through all the different comments if you want. But let's hop over into R, and I will show you all the code on how to do some of this stuff in R, and then we'll come back and kind of bring this full picture a little bit. So here we are in RStudio, and what we'll start off with doing is setting our seed, which I talked a little bit about last time, and we're going to be loading two packages from the start. We're going to be loading the ergom package, which is, it stands for exponential random graph models, but you don't need to know that for this lesson. And then as well as the intergraph library. And what we're doing with this is we're just grabbing a data set that's within this ergom package, and then we're using intergraph to connect that into an igraph object, which we talked about in the last lecture as well. So here we are. We're grabbing our high school data set, which I talked about just a little bit ago. We'll detach to the packages that we don't need anymore, and then we'll load in our favorite package, igraph for network analysis, and then we'll connect that data as an igraph object. So what we have here, if I run this, and you can see it already, we have two graphs, and this one looks really gross, so we added a couple different options here. And so here is our high school data. And just to repeat what I said before, our high school basically sent out a bunch of different surveys, and everybody listed all of the different friendships that they have. So this is a directed network with a couple different variables that we'll talk about here in a second. But we have 248 nodes with 1,197 connections between those, or edges. And we have a couple different isolated students that have no friends that they listed and no friends listed them. Kind of sad to think about, but there might be a good reason for this. There might be these kids might be in a different school system or program, or maybe they're just connected to the school but they stay at home or something like that, but you could investigate this more. The different characteristics that we have with this data is we have grade, race, and sex. So each of these, we could run this. I'll show you them real fast. But the grades for this school is between 7th to 12th grade. And then all of the race variables are listed here, where B equals black, H is Hispanic, O is other, and W is white. So pretty rough chop of the racial makeup of the school, and then just 1 and 2 for male and female, and we see that it's exactly equally split, 124 each way. It's probably because this data is made up. But yeah, so we have a couple things to look at with this data. And if you want to know more about everything I just kind of breezed through there, go back to the last video and in the first of this series, and you can learn a lot more about how this data is set up and how we just kind of read that stuff. But when talking about degree centrality, which is our first form of centrality, this is just a number of connections that one has. So for directed networks, which we're talking about here, the inwards degrees are the connections pointed in towards yourself, and outwards degrees are the connections that you pointed outwards. So for this data, it would be if I put my 2 best friends on the survey, those are 2 outward connections, so those would be picked up by outward degree centrality. And then inward degrees would be anybody that listed me. And we can specify this through having, well, first, this function right here is kind of the go-to. So we have this degree function. And I'll be saving these all as various objects because later on we're going to look to compare all these different measures of centrality. But if I just run this using the degree function, we can notice that we have that graph object now, the degree vector, as well as the degree score, so the number of connections that everybody has, all throughout our data set for every row. And so using the head function, we can see the first 6 observations. And then using summary, we can see all the summary statistics of the degree centrality measure. So the average degree centrality, or the mean, is 9.6. And this would be one statistic that you would compare to other networks or other papers that you've read or other school districts, or measuring this over time. So this would just be one form of statistic that you could use to measure centrality at your school. But as I was talking about before, we can create in degrees and out degrees. What we would do to do this is there's an option within the degree function to set the mode. And in the mode for this, we would just set in or mode out. And for these, I created some very rough histograms with 20 different bins. And so if I run these, see, for our in degree vector, we have this sort of rightward skew, where in average for in degree vectors, we have a mean of 4.8. For out degrees, it's similarly 4.8. But the graph looks a little bit different. Still this long right skew, but we can see we have some more outward degree population at the far right fringe than we did here. But basically the same. I mean, the descriptive statistics are pretty similar, if not almost exact. Just the maximum is a little bit different for outward centrality. So we can't really derive too much from that. But that's not the only form of centrality. There's a lot, and we'll just be going over the main few here. We won't be able to cover every single one of them, and we don't really have time to cover all of these in excruciating detail, but we're just trying to cover kind of the summary of everything. So next up is eigenvector centrality and PageRank centrality. You may be familiar with eigenvectors if you do things like k-nearest means or machine learning stuff. But all we need to know for the purposes of our lecture here is that these measures are not only capture the number of connections, but the importance of these connections as well. We should just remember here that eigenvector, this function should be used for undirected networks. We're going to go ahead and use it anyways. But PageRank is best for directed networks. So let's go ahead and run this. How we would do the eigenvector, it would be EV cent for eigenvector centrality. And then from this, we could get the vector off of it and store that. Let's run this. We see it's very similar to before. Different unit of measurement here, though, so the interpretation kind of changes between the events, but we still have this long rightward skew. Again, we would mostly use these for undirected networks. So let's say perhaps we move to PageRank, which is simply page.rank. And if we run this, we actually see a slightly different distribution. We kind of have one hump or mode here, and we still have this long rightward skew, and again, the scale changes. But you would interpret these numbers very similarly across units of measurement, I mean, they're all measures of centrality. They just report things slightly different with like different underlying math. Um, yeah, so we'll be comparing all of these here in a second. But there's one more called closeness centrality, as well as betweenness. Well, let's talk about closeness. So this is a measure that will measure how far or close a node is from one another. And we could use this the same way as before with degree centrality, where we would mark the inwards or outwards connections. But here we'll just run closeness. So this will tell us how far or close each node is to one another. And we get some scientific notation, but let's pull up our histogram. And we see here that we have a far left end tail. And stop for a second and think about why this might be. That closeness would be basically 0 between some of them. Well, this is likely because of the isolated nodes that we had. If you recall, we go back to our network, we had these 9, I think there's 9 isolated nodes here, and so it's impossible to measure the closeness that they have between one another, or the centrality of isolated nodes. So closeness is kind of pulling this out and bringing to our alarm that we have this big gap here. And so let's do something about this. Let's cut out those isolated individuals. Now, normally I wouldn't recommend cutting out outliers in this way, but just to see what this distribution off here on the right is, we could break out the bins to like 100 or something and try to see that, but let's just, what I'll do here for this histogram is I will only take the observations that are basically above 0. And then we'll be able to view this histogram for our closeness centrality. We see here we have a much more normal distribution without that leftward tail added on. So here is how you would measure the mode in and mode out for these. So you would just essentially set mode in or out for the, similar to degree centrality, whether it's an inward or outward degree, but for closeness. If we run this, we can take a look at these numbers as well. You'll get some warnings, but it's only because of how we set the mode here. Our network isn't particularly set up to do this, but you'll notice here that we still have the outliers. But now we're just examining those directed networks inward or outward. So then betweenness, we'll notice here, is the extent to node which that they're connected to each other. Let me see what I wrote here. Okay, so that they're connected to each other node within that network. So the area between each node. And so this is really important when we assume that information is passing around a school. Maybe not for this case, but you see that betweenness centrality in a lot of papers on like gossip networks and stuff. I think for our purposes with this high school data, it's likely the best to use like a outward degree centrality and probably page rank. But just know that in a lot of these papers and articles, they'll just use every single kind of centrality measure and put them all in a table, right? So they'll list out a table with a column that has every single kind of centrality measure and then the descriptive statistics for all of those baked into an appendix. But maybe in the actual body of the paper, they will talk about the particular kind of centrality that they used for their analysis, if this is used in their analysis or not. I'm jumping the gun a little bit. For betweenness, it's simply the function called betweenness. And if we run this, we will find something pretty similar to what we saw at the beginning, a long rightward tail with betweenness being relatively low for people. And so then, our unit of measurement has changed again, and we have the mean betweenness between different nodes is 483. And so that would be the output from that variable. So let's just pause for a moment. Your head might be spinning a little bit. We covered a lot of different measures of centrality, all in a pretty short amount of time. And we also just ripped through a ton of code. So we can also just use multiple measures of centrality. And so imagine you're in this data science role and you go to the superintendent and you report, the survey you did, and you have all these students and look at this fancy network. And say you decided to use a measure of outward degree centrality. What is the superintendent really going to think? Or what is your boss going to think if you're at like a Fortune 500 company? Are they really going to care what kind of centrality, and do you really need to like argue why you used it? Maybe. Or maybe they're just going to ask you to do every single one of them and see what they all say. So let's do that part of the R session next, where we're just going to measure all of these different kinds of centrality and see how they match up to one another, and then kind of compare and contrast them. And ideally, in your situation, all levels of centrality would more or less tell you the same thing. You just may get slightly different statistical results. So let's find a cool way to measure all of this stuff with like a correlation matrix and then graph it a little bit, because graphs are cool. Let's do that part. So yeah, that was a lot of content. Let's go into comparing some of these different measures. And remember, I saved all of the data that we had as environment objects. So I'm going to do here is just create a data frame that has all of these different objects in them for our degree vectors in, out, betweenness, closeness, as well as eigenvector and page rank are added at the end there. And so let me run this data object. And if we just plot these, what we'll see is this really gross looking plot, but how you'd read this is essentially like a correlation plot where you have all of the different measures paired up to one another. This is similar to using the core function, COR. If you're familiar with R, this is kind of a go-to for most things, where you get the correlation metric between all of these as kind of an adjacency matrix, but just for correlations. You can see here that most of these are positive trends, so these different measures are relating to one another pretty strongly. Like this one here is pretty much just a line up the side from a kind of linear sense, but nothing too crazy, no like giant blots of information. Everything kind of seems to be working as it should be. But we can lay this out and visualize it even a little bit more if I use library scales as well as this layout function. And so what this layout function is doing is basically just setting up the layout for how we want our data to be looking. And then we'll use library scales to basically make this plot. And so it's a little bit small. Let me see if I can make it a little bit bigger for you. Nope, not really. Oh, there it is. So here what we've done, let me run through this plot. We have rescaled, all right, so for the color, we set the color to be what grade the students are in. And so we see that there's the gray grade as well as orange and blue and green kind of spattered in there. But we can see some pretty good clustering between these different grades of people. And so that's suggesting that they're pretty well connected within their grade, which makes sense. We're rescaling the vertex sides based upon their inward degrees. And so a larger bubble here would be somebody with a ton of connections pointing towards them. And so this is a pretty accurate measure of popularity in a high school sense. Certainly much more than what we talked about in the last video and at the start of this video. So these large bubbles are people that have said, yeah, that person's my friend. And there's been so many of those people to say that now the bubbles are larger. And so we can kind of see who the, for lack of a better word, the elite are within their different age and grades here. Set up the arrow size and the width to how I want it, and set the vertex label to no, so we don't have a bunch of labels everywhere. And then the layout, you'll notice, was this layout here, where I specified with this function on that data set to be that layout. That's how we made that graph. And if I put in a legend, since we're just kind of using base R, we can build stuff without plus signs like we would use in ggplot. But I'll just put a legend on this one here. Let's send the legend so we can see our grade. If you're interested in seeing this code, I know I'm going through a lot of stuff pretty fast, but all of this is shared in my GitHub, which you can find in the description. So that way you can pick through some of the comments and some of the coding a little bit more. Feel free to do that if you have any coding questions, because I'm likely skipping a bunch of stuff like categorical _pal function, for example. But if we look at the page rank plot, see things don't really change that much. Some of the sizes changed, of course, a little bit because that's how we're namely defining the size of the variable is through the centrality measure. But if we continue doing this sort of graphical comparison, we can look at Betweenness, which the sizes just kind of shrink a little bit, but mostly the same. Closeness, which the sizes all got a little bit bigger, because remember the measure of centrality for closeness was a little bit larger, but you could very easily divide that and get the ratio out a little bit more comparatively. And we haven't ran all the graphs, but this is kind of two different ways that you could compare things. You could plot all the graphs side by side and then assure the reader or business leader, or whomever, that the results don't really change that much based on the measure that you use. Or my favorite is just to go back to this plot where we plot all the measures and say, look, I mean, these are so heavily correlated that it doesn't matter that much which one we use. I've used outward centrality and page rank because mathematically those make the most sense. And usually that will be enough to ward off any skepticism for centrality measures. But if you want to know more about centrality, again, I would pull up the GitHub page and probably look a little bit online about how these functions are coded and some of the math underlying these functions. I've tried to dig a little bit into that in the comments if you read those through. But yeah, that's pretty much our comparison there. So now let's come back full circle. We went out, we collected all of the different network data, we went through each type of centrality measure, and then we compared all of the centrality measures to each other, presented all the information up, and the superintendent still doesn't really care. All they want to know is, does that information correlate to their grade? And we have that grade variable. So I'll put together a graph on this and maybe a table, and I'll put it up here on the screen now. That's what you would present to them. But now we know a lot about centrality, and that's pretty exciting. So next time we're going to be looking more at like community detection, where you can specify the number of groups, and you can do this a bunch of different ways. It's kind of similar to machine learning and k-nearest means, if you're familiar with that stuff. If not, don't worry about it. Next time we'll talk a little bit about all this stuff. And yeah, I'll see you over there. If you have any ideas on how you can do this stuff better, let me know in the comments. I'll be reading through all of those. And yeah, I hope you learned something. I'll see you guys in the next video.